Everybody. Thank you so much for tuning into the second AI Here and There event, this time focused on artificial intelligence and sustainability. My name is Mona Sloan. My pronouns are she, her. I'm a sociologist here at New York University, where I work on inequality in the context of artificial intelligence, design, and policy. I am a senior research scientist with the NYU Center for Responsible AI. I also teach at the NYU Tandon School of Engineering, and I am a fellow at NYU's Institute for Public Knowledge. And I also edit the text section for public books. This is hosted between the NYU Center for Responsible AI and the Swiss Consulate in New York City. And we are absolutely thrilled from the NYU side to be working with the Swiss Consulate. It has been wonderful so far and really good fun. And I hope this good fun translates into the second event as well. It certainly has for the first. And I am extremely excited for today's conversation. And you will shortly see why, because this is a really interdisciplinary conversation. Now, before we get going, please let me remind you that we are recording this event today. Please let me also acknowledge that I am standing on the unceded land of the Lenape peoples. And I ask you to join me in acknowledging the Lenape community and to commit to beginning the process of working to dismantle the ongoing legacies of settler colonialism. Now, on to today's topic. Artificial intelligence and sustainability. Now, I think it's fair to say that artificial intelligence at this point is an integral part of our everyday lives. As such, it plays a role in the mounting climate emergency. Even though we tend to think of digital technologies as somewhat climate neutral, they in fact can have a significant carbon footprint. And that, of course, is just one sustainability concern when we talk about artificial intelligence. For example, a very powerful AI domain is natural language processing, or NLP, which is very broadly the automatic manipulation of natural language like speech and text by software. Think about chatbots, or think about autocorrect software, or products like Grammarly. Training a single large natural language processing model can have a significant impact on the environment. In 2019, researchers at the University of Massachusetts Amherst analyzed various natural language processing training models available online to estimate the energy cost in kilowatts required to train them. Converting this energy consumption and approximate carbon emissions and electricity costs, the authors estimated that the carbon footprint of training a single big language model is equal to around 300,000 kilograms of carbon dioxide emissions. This is roughly in the order of 125 round-trip flights between New York and Beijing. At the same time, however, it's important to remember that artificial intelligence can help mitigate the effects of the climate crisis. And today we have excellent experts on that topic to talk about that today. For example, AI systems can help reduce the effects of the climate crisis by supporting smart grid design and sustainable agriculture, as well as the development of low-emission infrastructures and the modeling of climate change predictions. And we'll be hearing about that a little later. Now, enough from me. Without further ado, please let me introduce our panelists from both sides of the Atlantic today: Carol Plummer, Fernanda Perez-Cruz, Eric Nast, and Venkrantamani Balaji. Now, Carol Plummer is the co-founder and CEO of Vivant, an ag-tech business that aims to deliver autonomous horticulture systems for growers and speed up product development for agrochemical companies so that we can grow healthy food with less environmental impact. She is a very experienced entrepreneur and has always focused on deep tech innovations. She has lots of B2B experience in B2B markets, as well as experience with complex distribution channels. And she says she's happiest working with colleagues on solving challenging problems. And I'd say, the climate emergency certainly is one of them. And we will be hearing about plant signals from Carol today. Welcome, Carol.
Thank you.
We We'll also be hearing from Fernando Perez Cruz, who is an adjunct professor at the Department of Computer Science of ETH Zurich and chief data scientist at the Swiss Data Science Center. The CDCS, the Swiss Data Science Center, is a joint venture between EPFL and ETH Zurich, and its mission is to accelerate the use of data science and machine learning techniques within academic disciplines of the ETH domain, the Swiss academic community at large, and the industrial sector. A multidisciplinary team of senior data scientists and experts in domains such as personalized health and medicine, earth and environmental science, social science, and digital humanities, as well as economics, enable collaborations on both the academic side and the industrial side. So you will be hearing from Fernando about a lot of interesting applied projects today. Welcome, Fernando. It's so nice to have you.
Thank you, and good afternoon to everyone.
Thank you. Also on the panel is Eric Nast, who is an assistant professor in geography, environment, and geomatics at University of Guelph. And I had to learn how to pronounce that. He researches how data technologies inform conservation, drawing on the fields of political ecology, science, and technology studies, or STS, and digital geographies. New kinds of generating sensors and data synthesizing algorithms are becoming central to everyday life and may prove transformational at a policy level as well. What Eric says is a key challenge for geographers in the coming years is assessing these technologies' promise to help society solve sustainability issues related to food security, climate change adaptation, and ecosystem services conservation. Eric is also a member of the coordinating committee for the Environmental Data and Governance Initiative, which works to build civic technologies and infrastructures that make data and decision-making more accessible, and tracking how the US federal government portrays climate change and other issues on the web. Welcome, Eric. Thank you so much for joining. Then also on the panel is Venkatramani Balaji, who is at Princeton and is heading the modeling systems division at Princeton's University's Cooperative Institute on Modeling the Earth System. Science, since 2003. He's also an associate faculty at the Princeton Institute for Computational Science and Engineering and the High Meadows Environmental Institute. He has a background in physics and climate science, and he has also become an expert in the area of parallel computing and scientific infrastructure. He is co-chair of the WGCM infrastructure panel, tasked with developing scientific requirements for the global data infrastructure underlying the climate model intercomparison project, a pillar of the IPCC assessment reports of the state of the Earth's climate. Welcome, Balaji. Thank you so much. A lot of complicated names, but I'm sure we will dig a little deeper and learn more. Thank you so much, everybody. Now, if you would allow me, a few words in housekeeping. So we will be having this panel discussion for about 30 to 40 minutes. You are absolutely welcome and encouraged to put questions as they pop into your head. You can pop them into the Q&A chat that you can find in the bottom of the screen of your Zoom window. After the sort of 30 to 40 minute panel discussion, I will be starting to ask the questions that you pose. If you would please indicate who the question is for, who of the panelists the question is for, that would be wonderful. If you just want to ask a general question, I will make a decision about who I will ask this question. Now, I would like to start the conversation with sort of the more challenging part, which is simply asking, what are the different problems and challenges that AI poses when it comes to sustainability? And Eric, you've been kind of working on this thorny and, continually emergent question for a long while now. And I would love to hear from you. What are the different ways in which we should even start thinking about how AI infrastructure is embedded into the world and how it affects the planet?
Sure thing. Well, thank you so much. Thank you for inviting me. Thank you for everyone for showing up today. I do want to acknowledge that my thinking around this and work in this domain is alongside my collaborators such as Dr. Ruth Machen, Dr. Emma Colvin, Dr. Jenny Goldstein. So I just want to make those acknowledgements up front. And sort of the main theme of my remarks across all of our conversations today are really around what are we measuring? And in this first kind of round of discussions, as you suggest, Mona, how are we evaluating the effectiveness of AI for sustainability? And before I get to this question around, the embeddedness of AI in the world and the kind of environmental consequences or potential impacts of AI, I do want to start with the promise of AI for decision making in particular. So I'm a social scientist, so I'm interested in how artificial intelligence and machine learning, how we can actually incorporate that into decision-making processes. As a geographer, I pay a lot of attention to questions around spatial precision. So that's actually a really key domain here is the ability to use AI feature identification, helping us sort through satellite imagery of wildlife, and so on to pick out individual entities. So decision-making can be better targeted to specific areas of concern. So an example would be like identifying single trees from satellite imagery instead of forests in order to build better forest inventories, inform efficient management practices, or more precisely, at like a meter or less resolution, mapping land cover and watersheds in order to understand the areas that contribute most to flooding or nutrient loading. At the same time, AI offers some prediction forecasting capabilities and maybe more generally speed and responsiveness. So running new conditions through the model and updating, there's a constant learning that's possible. So like in electricity grids, sort of being able to dynamically adjust to demand or load. It's not just precision, so AI offers some potential around kind of more holistic analyses, integrating a wider array of factors into analysis. AI and machine learning can gather potentially good proxies for data we've always wanted but never could get. So like estimating demographics in parts of the world where census data can be hard to come by, and that allows us to kind of bring together social and environmental data into climate adaptation. And then also objectivity. So, theoretically, the data themselves, would suggest in decision-making that this is the right course of action, potentially removing human bias. So that's kind of promise. Mona, you've already mentioned, there's often when we think about the environmental embeddedness or outcomes of AI, we think about the energy use required to train and deploy models. And certainly that's there. I'm going to actually set that aside and just raise a couple of other points really quickly. Some questions that we need to maybe get some better research on. So water usage. We obviously to power the data centers that are AI models are run on and the processing data through. There's the thermal power generation that comes with that and the water used for that, but also to cool those data centers. And that may not necessarily be a big drop in the bucket nationally in the US, but it can be locally significant, and sometimes that's even drinkable water. Generally, you don't really have good numbers on that, but that is a source of something we need to think about, something we need more research on. There's also the hardware questions. So just even building the infrastructure for AI involves rare earth mining, e-waste disposal at the end of life, and these are things that we also need to keep in mind when we think about kind of the environmental consequences. This isn't to say that AI isn't worth it, but that we do need to understand these trade-offs and these kind of potentially paradoxical outcomes.
Thanks so much, Eric. I really appreciate that you sort of teased out the tensions here so nicely. And you spoke about sort of kind of how can we use these technologies to understand the environment a little better. And so I would love to toss it over to Carol and ask you, Carol, you work, at a very particular intersection of artificial intelligence in the environment, which is agriculture. And your company is developing biosensors and other services for plant researchers, for professional plant growers and farmers in all types of growing environments. Plant signals and artificial intelligence, that sounds very futuristic and extremely interesting. Can you briefly explain what that means, and perhaps then also tell us about the impact of agriculture on the planet at the moment, and also the challenges of using artificial intelligence in agriculture?
Certainly. Thank you very much, Mona. I'll try to answer those questions briefly. First, I thought it was interesting what Eric said about thinking about the whole life cycle analysis of the tools that you need to bring to bear to use AI. I think as a person, I'm pretty optimistic, and I really believe in tech for good. And I think that AI is opening up some really exciting possibilities for technological advances. So for us, we are working with plants, as you say, and we're looking at plant signals. So all biological systems at the cellular level, when they're exposed to stimuli, create some kind of response. And they use these responses to regulate growth or to regulate reproduction, to mount defenses. And so we really look at biology through the lens of information theory. So what information is being gathered, transmitted, processed, and what are the visible responses we can see to that? And I think for us, we think by better understanding how biological systems are using information, we have really a chance to help improve the health, not only of people and plants, but also the whole biomes that support all of us. In terms of where we might have an impact, well, on a global basis, agriculture has a huge impact on the environment. Uses 50% of the land, 70% of the fresh water, creates a third of the greenhouse gases. So if you want to look for a place to try to impact on the environment globally, agriculture is a good place to look. So how are we doing that? We are, as I say, we are recording these small signals that are emitted by cells in response to stimuli, and we are processing them using AI. And so these biosignals that appear in people and plants and bacterial communities are hugely complex, and they vary in time and space. And whenever you're dealing with biology, the system is not the same from one moment to the next. So the plant ages, the plant has more genes that are upregulated or downregulated in response to a stimulus. So for us, one of the big challenges we face in analyzing these signals is the fact that plants are adaptive organizations. So the response to the stimuli this time is not the same as it was last time. And so to interpret these signals, we need big computing power. And AI is just a magnificent tool for being able to analyze and interpret these signals. People have been able to record these signals for more than 150 years, but we couldn't do much with them because we didn't have the tools we needed to analyze them. And machine learning and AI is the tool that's going to enable us to make some really big scientific breakthroughs. And we're focused on plants because they have some really special properties that I think are, open up some great opportunities for technological advancement. But that's a little bit about what we're doing. And some of the challenges we face are that the signals are complex and that they change in response to the stimuli. So I think all biological signals are like that. So that's one of the challenges biologists using AI face.
Thank you so much, Carol. I really appreciate it. Also, you using the metaphor of using information theory as a lens through which you look at biology. That made a lot of sense. Balaji, you are facing similar issues, I would assume, or questions in your work. You're also dealing with very complex, adaptive, ever-changing systems. And so as far as I understand, computing, and Carol has just briefly alluded to that, computing and artificial intelligence has changed forecasting significantly, which is, I think, one of the aspects of your work. But there are also new limits to this progress, some of which you say have to do with Moore's law and the increasing complexity and cost of the model. So we're not just only dealing with complexity sort of in the systems that we observe and analyze, but also increasing complexity of the systems that we use to do this observation and analysis. Can you tell us a little bit more about this dynamic and how it sort of features in your work?
Sure. Thank you, Mona. Thanks. And it's both the other panelists have given me stuff I can work off as well, because they're both extremely relevant to what I'll talk about. I'd like to give to talk about this in the context of a brief history of how forecasting, weather forecasting, climate, meteorology in general came about. And there's a pivotal event in 1950 that's kind of very important. So prior to that, if you think about forecasting, it was based on many rules of thumb. You probably seen the Farmer's Almanac, which is still released every year, which gives people, just based on common sense knowledge, agriculturists were able to give certain amount of forecast. You've heard of sayings like red sky at morning, sailors take warning, red sky at night, sailors delight. And what that really refers to is where the clouds are. The clouds are, and if you're in the northern hemisphere and the clouds are in the west, you're probably going to get bad weather soon. So red sky at morning is a warning signal. On the other hand, if the clouds are in the east and it's open in the west, then you see a red sky at night, you see the sunset. That means that it's clear weather on the west of you, and the weather systems always come from the west. So these are all rules of thumb that people use. So we can think of those as early forms of pattern recognition. So people would be pretty well able to tell just from looking at the data, holding a finger up to the sky, what the weather was going to be like the next day. And even formally, the way forecasting was done was actually meteorologists would take little bits of data from here and there, which they would get from weather stations, which have been around for a few hundred years. And then they would draw by hand these contour maps. They would draw maps. And when they saw the map, meteorologists by experience, they would know what would come next. They'd seen many maps of this kind. So this is what we would call pattern recognition. And this is how weather forecasting was actually done. It's not like the physics was unknown. The physics that governs this is, or the physics of the atmosphere and the ocean, is what's called fluid dynamics. And the equations of fluid dynamics, which are called the Navier-Stokes equations, have been known since the early 19th century. But there was no way to actually compute and get a solution to these. So people just worked with patterns. Another really good example is when you think about not just weather, but like why we have droughts in certain years. I mean, these are all things that affect humans in very major ways. Like if you take India, for example, India is very dependent on the monsoon. And some years you have a monsoon, some years you don't. And if you don't have a monsoon, so there was a meteorologist called Walker who worked in the 19th century. He was the chief meteorologist for India, appointed by the British Empire. At that time, of course, a drought was a huge cost. I mean, in colonial times, drought meant famine, lots of people dying. Nowadays, people don't die, but it perturbs the social fabric quite a lot. So it's very important to understand why monsoons come certain years and not others. So Walker had access to a lot of data. I mean, the sun never sets on the British Empire, as you recall. So he had data from all over the world. And he did what we would today call machine learning. He didn't have a theory, but he just looked to see whether he could predict the drought based on some data he found somewhere. And he found something which we now know as the phenomenon is nowadays called El Nino. It's related to fishermen in Peru. Some years they get lots of fish in winter around Christmas time, and they attributed it to the child, El Nino. So people used to do pattern recognition for the longest time. In 1950, there is this pivotal event, which is von Neumann invents something called the digital computer. And that completely transforms the landscape, because now you're able to actually take these equations of fluid dynamics, and if you know what the initial conditions are, you can actually solve them on the computer. And that actually took forecasting to a completely new era, which is the era of physical forecast done on a computer. And that event was completely transformed the landscape. So we went towards now having actually computing be the basis of doing forecasting. And von Neumann actually started, he also said something which he said, like, what would happen if you take a forecast? In fact, the very first forecast models were run in 1950 on one of the very first computers that ever existed, ENIAC. Anyway, he said, what would happen if you ran these for a very long time, which he called the infinite forecast? And people, Suki Manabe was a scientist who's still at my lab, and he's still, I mean, he's emeritus now, of course, but he still comes by. And if we were actually in a lab, I would meet him once in a while. He took these models forward, and he actually showed, he proved a result that was actually Eunice Foote is a scientist from the 18th century who did this experiment where she said in a glass jar, she put a lot of CO2 and shone sunlight on it, and she found that it warms up. And she speculated that it might actually apply to the planet. If you keep adding CO2, it's going to warm up. That result was attributed to men for many hundreds of, for 100 years or so. That's a different story. But anyway, Manabe was able to show using these new computer-based models that you can show this result, that if you keep adding CO2, the planet is going to warm up. So we had computer-based models now, and the computers were big, giant machines for the longest time. Then around 1980, of course, we have the Apple II, we have PCs. Suddenly we have Moore's law taking over and computers become very cheap. And we're able to build bigger and bigger models. That means you're solving the planetary climate and weather and all that with more and more pixels. So you're getting more resolution in your models. But what's happened is that, that the reason why computer power keeps doubling, which we call Moore's law, which Mona referred to, is because transistors keep getting smaller and smaller. But we've reached a limit of that right now, and we cannot miniaturize things anymore. And the energy consumption of these computers, these big computers, has become very large, which Eric alluded to. Some of these things are modeled. So we have taken a turn in our field towards machine learning. What we are hoping to do with machine learning, it's still very much a research project, is that these models are too expensive to run. So can we learn to do what I call emulation? Can you emulate the behavior of these very complicated models by using machine learning? So that gives us actually models whose carbon footprint is less. So if you think about the problem that I mentioned of resolution of a model, each time you double the resolution of a model, that means where you had 1 pixel, you have 4 pixels. The amount of computing, the amount of carbon you use to do this computation keeps growing up at a pretty astronomical rate. So we are hoping that ML will actually help us build these models that are cheaper, easy to run, to explore and understand the planet. So that's one of the ways in which AI comes in. So I'll stop here and we can return to any of these subjects later.
Thank you so much, Balaji, for explaining this very complex topic so succinctly, and also linking this back to the human practice of identifying patterns. That's as a sociologist, I'm extremely excited about that. But I want to stay with the sort of applied side just for a moment. And Fernanda, I would love to hear from you. As somebody who works really at the intersection of data science and sort of applied not solutions, but maybe questions or challenges in the context of data science in the industry. I would love to hear if you would want to share any experience or insight you may have on using data science in the context of environmental science, and sort of maybe a reflection on the limits of data science in that context.
Thank you, Mona, for the question. I think picking up where Balaji left about the climate models, and that's probably one of the limitations that we're going to have in data science. There is the models that we are using for climate and weather prediction. They're trying to simulate more and more smaller regions, and they have that problem of that the physical models are very computationally intensive. And using machine learning, you can emulate them. The other thing that is happening with these models is as they get to a smaller area or volume, we are getting now to the level that we can resolve the vertical component. And that is going to be extremely useful. But one of the aspects of these models is that they generate so much data that now we don't only have a computational problem, where we have a storage problem. They are getting petabyte of data per month. And the amount of being able to resolve that data and be able to use it in order to understand what is going on is one of the challenges that we're going to have to do with data science these days. So it's not only the computation, but how do we manage that amount of data? And the other thing about the thing that Balaji mentioned about weather and climate, there is now we are able to. If we get the global temperature per day, even though climate is what you expect and weather is what you get, now from the weather of every day, we can know that climate change have occurred. So there is enough signal throughout the whole planet. You might not know it in New York, you might not know it in Zurich, but if you take the temperature all over the world, you're able to to get that that information. And that's one of the results that we got in our lab last year. Regarding the challenges of data science and artificial intelligence, there are two things that I would like to mention here. One of them is we know the relation between CO2 and temperature. There is a clear relation that there is more the CO2 that we have in the atmosphere, the higher the temperature that we get. But one of the challenges that we have is how that relates to the water cycle. The water cycle is how the water goes from the clouds to Earth and go back. I don't want to go through the whole process, but understanding how climate change is changing the water cycle is more complicated because there is not a single component. There is all these things in the US that you get, the hurricane season. We get, when you get very few hurricanes, they say that we have very few hurricanes, but much stronger than we got in the past, and they attribute that to climate change. Like last year, instead of getting you got very large one, but also many of them, and then they attribute that to climate change. How do we understand all of those things? Those we don't have the tools for understanding that causality. How they're doing the attribution of the changes is one of the things that is still a challenging problem within data science and artificial intelligence. The other thing that I think is challenging is something more down to earth. Most of the CO2 measurement that we have are very spotty. We only have it in a few places throughout the globe. So we know that CO2 is going up, but we don't know where it's being stored. So one of the things that we've been trying to do is create a network of CO2 sensors across Switzerland and especially in Zurich. And that will understand how the CO2 flows through the country or through the city of Zurich. Most of the sources of CO2, we know them, but most of the sinks where is that CO2 being stored is something that we don't know. It's in our lakes or in our rivers or in our plants, as Carol probably can explain much better than I can, or in our seas. How that model is going to be very important to understand. The issue of measuring CO2 is that it's usually very expensive, and we're trying to work with sensors that are not that good, not that expensive, but are also very, very noisy. And the issue with CO2 is that the signal is very small compared to the underlying value of CO2. So trying to be able to understand what are the changes around the 400 ppm that we have of CO2, it's a hard topic that we're working into resolve. Thank you.
Thank you so much for that, Fernando. That was fascinating to hear these very concrete and sort of hard questions about how we can sort of use or generate the knowledge on the climate emergency, what we can do with it, which is kind of the cue for a second round of questions that I would like to ask. And I just want to remind participants that you can pose questions to our panelists in the Q&A chat, and I will ask those in our Q&A part, which is in a couple of minutes. But I want to move on sort of from challenges to potentials of artificial intelligence and sustainability, and maybe policy, because with all this information, what are we going to do with it? And so I would love to hear from you, Eric, with these sort of tensions that you started us off with, and sort of everybody chiming in as well. What is a maybe more expanded framework of sustainability to account for these complexities and for these tensions? What kinds of questions would you say we need to ask, and what kinds of governance structures do we need in order to build on this wonderful knowledge and insight that is generated on the climate emergency by experts such as the ones on the panel today?
Yeah, thanks. So I'm going to pick up on that thread there of, what are the questions we need to be asking in order to ensure that, AI for sustainability, AI for good, that we're, deploying these things in ways that help us achieve what we want from them. Really AI is only as good as we are. And so, for me, the questions are really, what are we measuring in the data that we model and incorporate into AI? What are we measuring out of the AI in terms of outputs? and really who's doing that measuring. So, in terms of what's the data, we've talked a lot about environmental data. Oftentimes that, in many applications that can imply people. So I'm thinking about land cover data, for instance, where people are using that land. Or often our applications work on both environmental and social data sets. And so, there's this famous saying, data are people, who can be harmed by the way that they're represented in that data, in the way that we represent results and act on those results. Just a quick example of that, I'm involved in a project where we're trying to understand the enforcement of environmental protection laws like the Clean Water Act in the US. And in that project, we might be doing harm to certain communities if we say, hey, environmental enforcement or the enforcement of these laws is A-okay, based on the data that we have from the US Environmental Protection Agency. If we're not taking into account the fact that that data set has a lot of uncertainties, missing data, gaps in the data, so on and so forth, if we don't account for those things, and we just say, environmental enforcement is all well and good, then we might be doing a harm to those particular communities. So we actually have to, that's one question. What's the data? What's in the data? What's missing from the data that we're working on? We also have to ask, what are we optimizing for? Often applications of AI involve optimizing for specific outcomes. So, a good example there, maybe mundane example, getting data on city streetlights in order to target maintenance and save money. Maybe we don't need certain streetlights in certain parts of a city for whatever reason. Other examples might be minimizing greenhouse gas emissions, minimizing water usage, and that's all great. Efficiency is good, but there are also questions around equity. So we might make water distribution as efficient as possible, but we haven't necessarily ensured it's equitably distributed. So just, asking those kinds of questions of what are we actually optimizing for, and keeping that in mind is important. Kind of related example there is, there's these paradoxes, like the Jevons paradox, where, we can optimize for efficiency through AI applications, but that doesn't necessarily mean that we reduce overall demand if consumption continues to increase. Kind of in that vein example is there are applications of AI that in the oil and gas industry, for instance, that help make those operations more efficient, which is good, but it means we're still continuing to consume oil and gas. That's not necessarily a problem inherent to AI, but it is something that we need to recognize. And there's also questions around reliability, not just equity. So, reliability is often an important social goal, but can be difficult for AI, which is good at recognizing things it's already seen before, maybe less so at new, unpredicted, edge events or disasters. But that's a problem because oftentimes as a society, we want something that's reliable. And kind of the final question then that, comes to mind here is, who's able to work with and implement artificial intelligence applications. So, some of the issues I've just talked about can perhaps be really addressed if we improve the capacity of civil society groups, nonprofit groups in the Global South use AI. There's certainly a lot of AI development already ongoing in those sectors and places, but there is this question about democratizing AI. There's Microsoft AI for Earth, which is aiming at that and enabling the capacity of groups like the Chesapeake Conservancy to use AI to better understand flooding and nutrient loading in their region. But it still remains to be seen how widely it is possible to democratize AI in that sense. So those are just some of the questions that come to my mind in thinking about policy around AI moving forward.
Thank you, Eric. And that sounded also kind of like building, policy infrastructure in a sense. So infrastructure seems to be sort of a big topic at the moment. Carol, let's sort of hear from you if somebody was like actively at that intersection, and especially at the intersection of sustainability and science. How can AI help with scientific discovery from plant, on everything pertaining to plants, and how can this help specifically with sustainability efforts, maybe also with a view towards policy, or at the very least, discourse around policy?
Thanks very much, Mona. I think it's a really interesting question, and I certainly, heard interesting comments from Eric, Fernando, and Balaji that I'd love to respond to. I guess first of all, I think plants are a really good test system from which we can learn things. So you think of Gregor Mendel and his peas, and eventually it leads to genetics and the study of genetics. And for us in particular, plants are a really great model system because we can measure plants when they're healthy, and then we can expose them to some kind of stress. It could be, heat stress or drought stress, or it could be a serious pathogen or an insect attack. So we can measure plants when they're healthy and measure them when they're under stress. And we can learn to find differences in the signals that they emit in those two conditions. And that helps us diagnose those conditions earlier. And I think there's several messages I want to give that come from being able to work with plants in a healthy state and a stress state. And if you think just about agriculture and making agriculture more sustainable, if we can use systems like ours to diagnose crop stress early, it means that we can treat those stressors. We can optimize the conditions in a more environmentally preferable way. So if you diagnose a pathogen early, you can treat it with a less toxic chemical, or maybe with some other kind of beneficial insect or something like that has much lower environmental impact. So early crop stress diagnostics means more effective crop protection solutions, improved yield. With the improved yield, you could actually maybe repurpose land for something else, or use less water or fertilizer. So I think diagnosing crop stress or crop diseases early really can help improve the sustainability of agriculture and improve the security and safety of the food system. So that's, something where we can use an advancement in plant science driven by AI to improve sustainability of agriculture. But I think in some ways, for me, it's even a broader question than that. I think, again, plants, because they don't move, are a really great model system for looking at interactions between the environment, whether that's in the air or in the soil, the plant system itself, and the related systems, the bacteria that lives in the soil, the pathogens and weather conditions above. So plants are a great example where we can apply systems thinking. So I think Fernando talked a little bit about, we know the CO2 cycle, but it's also impacted by the water cycle. And plants, again, are a great model system for this. And developments that we make using AI to better understand plants' responses to their environments, I think will lead to other advancements in, for instance, human medicine, or maybe in the way we manage biofilm growth. So the way we understand biofilm and manage biofilm growth. So again, I think plants are a really interesting model system here. And I think they do force us to think in a systemic way. And that's, I think, when you think of policy changes, I think this is also another important message. I think trying to create policy that's focused on a single issue often results in less than optimal outcomes. So I think for us, when you think about crop protection products and reducing toxic pesticides, we think, oh, maybe they're all bad, so we get rid of them all, but then the yields go down so much that there's a lot more food stress, and food isn't distributed equally to all members of society. So I think thinking systematically or systemically is really important, and AI can help us do that. And so I think just people working with AI and thinking about different models can lead to some learnings that will make policy more effective. So that's a little bit about just what I wanted to say about how AI in agriculture can lead to more sustainable outcomes, both in agriculture and in related areas.
Thank you so much, Carol. And I really appreciate your notion of using plants to understand sort of, the bigger picture, really, almost as a lens or a way in. Balaji, I saw you nodding while Carol was talking. And so I would just want to throw it over to you and pick up on something that you said when we corresponded in preparation for this conversation today, which was we depend upon simulation to help us decide how to be custodians of the planet, as we don't want to experiment on the only one we have. Against the backdrop of your work and your experience, can you tell us a little bit more about how artificial intelligence fits into that?
Sure, I'd like to, and I'll also loop back to what I was nodding at while Carol was speaking. So, but first, Mona, I want to take issue with the title, which is Saving the Planet. Okay, so I'll just make this comment here. The planet is going to be fine. With or without us, the planet is going to be fine. It's going nowhere. It's going to keep revolving around the sun, and it's going to be fine. Many ecosystems are going to be fine. What we're talking about is saving our skins, finding a home for ourselves on this planet, where we can live in a way that we can coexist with everything else out there. There's something I'd like to point to students, and I'll put it out here as well. There's two places on Earth where humans are forbidden to enter, and we can leave it to the question and answers. People can try to think what these two are. And those two areas are thriving ecosystems. They're doing beautifully. The only thing you need to do to save the planet is to remove the humans, but that's not the solution we want. We're trying to make a home for ourselves here. So I hear billionaires talking about terraforming Mars. Terraforming means making an Earth-like climate. Let's terraform Earth first. That's really the key. That's really what we're trying to do here. So the thing is that we live in a period of around 10,000 years. If you look back at the history of the temperature of the Earth going back millions of years, the last 10,000 years seem to be kind of unique. Some people call it the Holocene optimum. The climate has been remarkably stable for about 10,000 years. It's very important because the whole of human civilization, agriculture, urbanism, all these things depend on having regularity, that you can predict year after year what's going to happen. That regularity is really, really important. And so we don't want to mess with this. We are doing it. So we are conducting an experiment right now. As I said, Unisfoot said that if you keep adding CO2 something, the temperature is going to increase. And climate modelers have been saying this again and again for decades now, at least starting since the 70s, that this is a serious problem. And we're doing an experiment. Well, let's ignore that and keep adding CO2 and see what happens. So that's the experiment we're carrying on. What we would like to do, if you take the analogy of clinical trials, I mean, we're living through a pandemic, so we've all had time to think a little about what clinical trials work. So we want to do clinical trials, but we only have one planet. So how do you do it? Because you need a placebo arm for a clinical trial. You need to do one where you add CO2 and one where you don't add CO2. So that's where Mona I said about simulations. We're doing clinical trials using simulations. We're creating models of the world, which we, through various tests, we say this is a pretty good simulation of Earth. And then we use it to model the past, the future, not only the two, but also what I call parallel universes, counterfactuals. An Earth where there was no industrial revolution never took place. We never added CO2 to the atmosphere. We call that the pre-industrial control. So that's your placebo arm for the CO2 trial we're carrying out on the real planet. So we're doing all these simulations. We're doing them with these big models that have become too expensive. And that's where AI starts to come in. And some of the key questions, if there are any AI people in the audience, particularly students looking to go into a field, I want to convince you that climate change is the key area to work on, even if you're only interested in AI. Of course, you should be interested in climate change because the crisis is existential for us. But it's raising some of the key issues of AI. So for one thing, we can use AI as a black box. We just give it a certain set of input data and it does predictions. And actually it's doing really well. There's many kinds of predictions, forecasting where black box AI machine learning is doing extremely well. But now we're talking about the kinds of things Carol is alluding to, where we're going to use it to make policy. We are going to look at some factual Earth and a counterfactual Earth and say we should do this rather than that. And for that, we need transparency. When the AI ethics question comes into it, why did you decide that this mitigation pathway is better than that one? Why did you decide? Who decided? Who's the winner? Who's the loser? So this gets back also to the question earlier about what are you optimizing for? So we need to know, we need to have transparency of what did you optimize for. So if you run models, then you can kind of say, I understand what the equations in the model are, and we can try to do that. So this is where it returns to the kind of things Carol is talking about. For the basic fluid mechanics, as I said, we can write down some equations, but the way vegetation interacts with the climate and how it, the evapotranspiration, for example, how CO2 and water vapor are exchanged between the atmosphere and plants through the leaves, all those we cannot write down a simple equation that tells you the answer. But there's some interesting veins of research going on using machine learning, where we are asking for the transparency part, for the explainable, interpretable AI part. We're saying, don't tell me just a map from the inputs to the outputs, which is the traditional AI thing to do, machine learning thing to do, but give me the answer in the language of mathematics. Tell me the equation that goes from your inputs to the outputs. And once I look at the equations, I can look at it and say, yes, based on what I know about whether it's physics or chemistry or biology, these equations make sense. Then I understand it. Then I can believe it, whether we're going into vastly different climates of the future or to parallel universes, wherever we go, I can trust the equations. I can take them with me because those things I believe would be universal. And so these are the ways in which we are hoping that AI will actually transform the field. But the challenge remains. I mean, Fernando made this statement, which is very important. He said, climate is what we expect and weather is what you get. We say that, but climate change means what you expect may no longer be true. So everything that you said, my data, this is what the Farmer's Almanac, it's the rules of thumb farmers have in their head. I know this is what happens in the last year. But as Fernando said, this is all changing. These people can no longer rely on the rules of thumb they know from observing the weather for a few decades. All that is changing. So the big challenge for AI is like, how do you deal with something where the data alone cannot tell you what you need? Because the data themselves are limited. We only have a few decades of really good data, the satellite era, let's say, when you have a lot of global data. But we need to understand how the system is changing before and after the amount of data we have. So AI has two challenges for us. One is to tell us in places where we don't really understand how it works, to tell us how it works. But the challenge for AI, which is why I think it's a great problem for people interested in AI, is like, how do you operate outside the bounds of the data that you have?
Yeah, and kind of pointing to the question, how can we think about this more as a sort of historical socio-technical system, right? Like as a, whereby the social and the technical are so deeply intertwined. We are coming up to time, so I have a last question for Fernando, then I have time for maybe 2 audience questions. Fernando, we've just heard about sort of the opportunities, but also the limits. And so maybe you can tell us, what are the very concrete ways in which you see society using AI in data science, more specifically, as a tool for sustainability, or as Balaji said, a tool for saving our own skin?
So before jumping into that question, I also want to reinforce a little bit what Balaji said. I think, and I think this is very important. I mean, machine learning or AI as a black box is very good when you already know what you're looking for. So let's say that you're Facebook and you say, hey, I don't want, I have pictures that I don't want people to upload to my service because they are pornographic or they are violent or whatever the way they describe the thing. They have a machine, picture good, picture bad. You don't need to understand. You're already solving a problem that you know what you want to solve. The only issue is you cannot have humans looking at pictures a billion a day. So for that, the black box is very good. When you're trying to solve the climate problem, you have 2 issues, and I think Balaji touched upon it. Black boxes are very good for interpolating data. Once you have enough data and you're moving into a closed system, deep neural networks are going to be very good at that. But if you're moving into a point in which you have to extrapolate, climate is moving into some direction that we don't know, the data can only tell you about the past. It can be very good at understanding the past, but you need the conjunction of the data and the physics to be able to extrapolate where are you going into the future. And I think that's one of the issues that we have with machine learning, that not only we need to extrapolate, but also we need to understand. And I think, again, Balaji said it before, is I think it's going to be very hard for a machine learning to give you the equation, but it can tell you why it's making that decision, in what direction is it moving towards, and why it believes that climate change is accelerating or deaccelerating, which is going to be one of the quick questions that we that we need to solve. So whenever we get to that point in which we need to understand, and this is basically the tool that unsupervised machine learning is doing, which is we don't only need to solve a problem that we already know that we have. We need to solve a problem that we don't know that we have. Okay, and I think this is where I'm gonna be a little bit adversarial to what Eric said, that AI is as good as we are. We expect AI to be better than we are, that is able to find things that we haven't found as human. And probably I can agree with Eric that we might not be there, because we don't have an AI or a machine learning solution that is able to generate hypotheses that we haven't found as human. And this is the key aspect, is when we look at all the data, maybe an automatic system might be able to find something that is very, very rare, that humans looking for patterns, as Balaji mentioned at the beginning with the almanac, they were seeing things that were repeated very, very frequently. But what happened if something only repeats once a year or once every 10 years? You might not be able to find it as a human because that pattern is not repeatable, or not repeatable within your experience. But when you have all the data that we have, we might be able to find those events, and those events might be meaningful in order to solve some of the issues. Going back to your original question, I think machine learning in many of these things, it's a help to climate scientists. It's not going to be the driving force, but it's going to be the tool that they can use. And that can use in two things: in understanding the model that Balaji is doing, but also is, once we have solutions, how do we optimize them? So once we have electric cars, we're going to have a lot of batteries from electric cars. Machine learning will tell you how to optimize that batteries in order to use energy in a better way. I think you pointed out at the beginning, how do we manage the grid? Once you have every car is electric and every car is connected most of the time to the grid, they can self to regulate the energy that we have. Machine learning, optimization algorithms with machine learning, like reinforcement learning or Bayesian optimization, will be key on doing those things. But in that case, it's only going to be a tool to the things that we have invented elsewhere. Okay, thank you.
Thank you so much, Fernando. I think that is a great sort of note to close on. I would love to ask one question. I'm going to synthesize two questions that I have in the chat that I think go together very well. And I would love one sentence per panelist as an answer to that question. The two questions I want to combine are: does the benefit of the solutions powered by AI offset the cost of running the systems, and how do we measure? And then what's the most important advice for somebody who is trying to implement predictive analytics in their product? So I think we can synthesize this into the following question: how do we assess how do we tease out the tensions that we heard about when it comes to making a very concrete decision as to whether or not we want to use AI technologies for a product, for any situation or any social environment that we find ourselves in, against the backdrop of the environment? What are the kinds of things we need to talk about in our everyday life, maybe even as decision makers? Eric, one sentence.
This is a tough one. I would just say that, awareness of what we're trying to get out of the application and what are some potential trade-offs, that's key. Just having those things in mind.
Thank you. Trade-offs. Carol, how to wrap our head around that?
Again, I think that's a tough question, but I think focusing on the objective that you're trying to achieve and being aware of the unintended effects of achieving that goal is what I would say.
Thank you. So sort of the topic of impact assessment, right? Yeah.
Exactly.
Balaji, what do you think?
Yeah, I would say that transparency and accessibility are the keys. Whatever solution we come up with, it should not be something, and the one reason why we go after energy consumption. So for these models are so expensive to run that they're only within the realm of a few. And then it becomes, we should not want AI to become an oracle that you go and you ask a question and you get an answer back. And you don't want that power structure to exist. We want to create tools that are in the hands of everybody. That's really what we're hoping to do with AI, is to make the complex behavior something, distill it down to something that everybody has access to in terms of both understanding and playing around with.
Yeah, and
that accessibility. Yeah.
And that links to a very, important and interesting sort of domain, which is literacy around artificial intelligence, right? Which conjures up a whole new bunch of questions around democracy. But I would love to throw this over to Fernando for a sort of last words around the how.
Okay. I mean, I will give the textbook analysis. I think one of the good things that machine learning does, and when we look, is at predictions. So you have your model, it makes predictions, and then you have your AI or your machine learning solution, and it does predictions. And if it does better than you expected, go for it. And if it doesn't, you shouldn't. But you should always validate. And predictions is the gold standard of any machine learning algorithm compared to how previously things were being done, which is understanding them.
Okay, thank you so much, which brings me to a close to today. Thank you so much, everybody. Eric, Carol, Balaji, and Fernando, thank you so much for joining from both sides of the Atlantic. It was such a pleasure to host you today. I learned a lot. I will definitely use the recording of this conversation in class because there were so many important and interesting points that were made. I appreciate the energy you brought to the space. I appreciate the attendees who came in as well. A big thanks to the Swiss Consulate, of course, and also to NYU Tandon for facilitating today. Stay tuned for our next conversation later in the month, which will be on health. And after that, we're going to talk about art. Thanks so much, everybody. Really appreciate it. I hope you learned a thing or two like me, and I look forward to staying connected and to seeing you for the next conversation. Thank you so much.
Thank you, Mona.
Thank you.
Thank you,
Thank you,
panelists.
Mona. Thank you, everyone.
Thank you.
Thank you.